So we're going to talk about what is so-called modern control systems. Modern in the sense of the tools that we use. From now on, we're going to be talking a lot about this kind of models in state space instead of just transfer functions. Transfer functions are tools to understand these better, but in modern control engineering, we use state space algorithms. So this is built heavily on linear algebra. So the tool that is very handy to analyze matrices, large-scale computations, etc. The motivation is very straightforward. If we think about a person, if we think about any structured systems, then there should be this concept of specific components inside the human. I have eyes, I have ear, I have different sensors, and I have arms, actuations for different purposes. So these are, I can consider my states, right? If I think about how United Nations is divided by 51 states, right? Then different states have its operation, has its organization. So in this large system, there are individual components inside that we can have some specific, we can build some sense, and we can analyze the large-scale system by having this concept of states, different states inside. So in what we discussed about static systems, dynamic systems. We said static systems, the current input is simple enough. It's only going to impact the current output. So yk is only impacted by uk at time k. And for dynamic systems, yk is dependent upon the past. But we didn't say like how much information we need from the past to be able to describe my system in a minimum sense. Like what is the minimum number of input, the past history that I need to use in order to determine the output exactly. I can use all the histories in the past, which is not economically, is wasteful in resources. So it's natural to ask our question, how much information from the past is needed, right? And that relates to the concept of states and minimum representation of systems. So the concept of state is the information that you need at time t. So if I say the state is xt, then this is all the information you need. You just need this state information at time t. So if you know how the state of the system is at this time, and you know like what is the input, what is the future input to the system will be, then this is the only thing you need to be able to see what the future will be looking like. The state at time t is the information you need at time t. That if you combine the state information, which is the information of the system, if you combine what the system is currently with what the future value you will give to the system, will completely let you define what is the future value of the output. Loosely speaking, this is the aggregated effects of all the past inputs. This is the memory that the system keeps at time t. Once you just need to take a look at this piece of information, then all the history, all the past history is accumulated in the states. That's the concept of the state. As an example, if you want to know if you have a mass, is moving at certain speed and it's have some initial position, it starts initially at some, let's say, y0 here, and right now it's at yt, and then it has a velocity vt. What is all the information that you need to be able to know where will be the future position of the mass? So we know this from physics, right? The position is integration of velocity. Velocity depends on the acceleration. So if you know, let's say I'm not applying any force to the mass, then I just need to know where it is now, plus what kind of friction I have on the surface. Then I can know exactly where the future position will be. If I know how much force I'm going to apply to the system, then similarly, I just need to know the current position and current velocity to be able to predict what the future will look like. I don't need to know this value at all if I just want to know what happens over here. Therefore, the states are the position and the velocity. Knowing these two, plus the future force, I know how the system will evolve. Yes?
Why is y0, y of 0 on top there?
It's a notation purpose. So when I wrote it, I say this is starting from some initial position y0. Yeah. But what I mean is precisely like this. It starts from somewhere. It has some current states. Then the states are the position and velocity. So from here, we know that this is the only thing we need, right? If I just know the velocity but not the current position, then I won't be able to know precisely the future position. If I know the position but I don't know the velocity, I won't be able to do the prediction. So I need both of them. And I only need both of them, only need these two. So the order of this system is 2, because the information in the states, I just need these two information. More strictly speaking, the order of a dynamic system is the number n of the state variables, such as position and velocity, that is both necessary and sufficient. I just need these two. I just need these n variables, and I can describe the system uniquely. So for a given system, the choice of state variables is not unique, but the order is fixed. So this can be simply understood. If I have a moving mass on the surface ground, I can use different units, right? I can say the speed is meters per second or inches per second. Then these two states are different. They're describing the same thing, but the unit and the value are different, right? But it's the same information. So these are two different choices of velocity state, but I just need as long as the speed information, position of information is there, I'm fine. Order is fixed, but the choice of state variables is not unique. So how we write in discrete time is as follows. So we say a system, input, output, and then the state variable, we usually use x, x1, x2, xn, etc. So the state is the minimum set of variables that I need to describe the system and its response for k equal to any time that's in the future. Just a different way to enhance the concept that this defines the system's memory. We write state space systems in this fashion. We say the state, if it's a dynamic system, then my current state will depend on my past state. So my current state depends on how I behave in the past. It depends on also what is the input. And it may depend on like the time. So for time variances, this is the most general case to describe a state space system. It can be time varying, it can be nonlinear, it can be as crazy as we want. But it's a function of the past state, input, and time. And then y, the output, is a function of the state, the input, and k. The general case description. For what we consider linear time invariant systems, then there is not a nonlinearity inside. The state is going to be linearly dependent on the past state, and this is linearly dependent on the input u. So the key concept here that's most relevant at the moment is that we must recognize A, B, C, D, these elements, these are now usually matrices or vectors at least. Because we talked about the states, it's going to be multiple states for system usually. Position, velocity, etc. So this is a vector. It has dimensions. Your input, it can be a scalar or it can also be a vector. So your input can also have multiple elements inside. Let's say your input is 2 elements. It can also be a vector. A, therefore, is going to be a matrix usually, has proper dimensions that when you multiply A with X, it can give you a vector on the left-hand side. So all these are matrices, and B can also be a matrix. So that's the main thing that we need to pay attention to. C can also be a matrix, such as this. If Y is a scalar, Y is just one element, and X is a column vector, then C is going to be a row vector. So if U is a 2 element, then D can be a 2 element row vector. Question?
On the bottom left, should input be U of k instead of X of k?
Absolutely correct. And you are faster than me. We haven't talked about this yet. U is the input. It's not X is the input. Y is the output. X is the state. This is a discrete time system. My next time instance, information in the next time instance, system state in the next time instance depends on the previous system property. If it's continuous time system, then we have differentiation here. So continuous time system is going to be derivative of x equals to ax plus bu. Y is cx equal to du. All the other things are analogous. So let's talk about this example and derive this state space description of the mass spring damper. We already talked about the states are position, velocity. Let's say the position is p, velocity is v. And we want to write out the model of the system. We already talked about, from Newton's law, how Newton's second law, the total mass, the total force is going to be the acceleration times the mass. Easy enough. It's going to be input u, this force, minus k times the position, minus, so this is function of t, minus b times the velocity from the damper. So we talked about this model previously. We're going to do a little bit of exercise and translate these, combine these ordinary differential equation functions into a state equation. We know from here the state, there are 2 states. I want to know like Vt, this is my second state, right? And Pt is my first state. I want to know how it's going to be related how it's going to be related. So I want to know the derivative of the state, how it relates to the current state and then the input. So that's the overall goal, is precisely here. We want to be able to derive this model where I have derivative of the states on the left and then AB on the right. The derivative of the position is the velocity, easy enough. So dp is going to be equal to vt. So in matrix language, dp is going to be the scaling of p is 0 and the scaling of v is 1. dp is going to be 0 times pt plus 1 times vt. And the dp, that's all. That's all about the derivative of the position. So it doesn't depend on u. This is 0. For the velocity, we know that dv t over dt is the acceleration, is this one here. We know from here, this Newton's law, how acceleration depends on p and depends on v. We can write a is going to be equal to, let's talk about p first, is going to be equal to negative k divided by m time plus negative b divided by m times v. And it also depends on the input u. So plus 1 times ut. So that is the state equation. So from here we can say, if we want to know what is the position, right? If I treat position as my output, let's say output y of t is my position, then it's just the state p v times 1 0. So it's 1 0 times the state over here. So that's the output if it's position. Yes?
Depends on 1 by m for the u of t.
One, say that again, please.
For dv of t by dt equals 80. It depends on 1 by m of ut, right?
1 divided by m of ut. Here?
Yeah.
Yes. Good catch. Cool. If I want to know the position as the output, I can do this. If I want to know, the velocity as the output, then I can simply do. So if this is position, if I want to know the velocity as the output, then it's simply a different scaling. So it's 0, 1 times p times the state. That's precisely here. This is the state derivation, state states model for the mass spring.